Math 2312, Chapter 1, Functions, Section 1, Functions and Function Notation, Video 6, Difference Quotient. This video isn't really about a feature of functions, but rather something you can do with functions that lays the foundation for a half of calculus. I believe we discussed this in class in some context, but a difference quotient for a function, f of x, is the expression f of x plus h minus f of x all over h. Before we get into a couple of examples, I want to give you the motivation behind the existence of something like that and kind of explain how it leads into half of calculus. In order to explain the motivation, I have to assume that you remember some things from an Algebra 1 or an Algebra 2 or possibly a college algebra class, namely how to find the slope of a line. The slope of the line is rise over run, which is really, just as a reminder, slope is second y minus first y over second x minus first x. When we review linear functions in greater detail, we'll formally and officially introduce, or rather reintroduce, how to calculate the slope of a line. But for now, in order to motivate the existence of a difference quotient, I want to remind you how to find the slope of a line. Difference in the y-coordinates minus over the difference in the x-coordinates. So what does this have to do with functions and calculus and whatnot? Well, the problem with the formula for the slope of a line is that it's the formula for the slope of a line in no other shape. In other words, if you have a line like this edge of this triangle, the slope measures how steep it is by taking the ratio of how far it rises compared to how far it runs. But that's assuming that your graph is a straight line. Well, line, not to be redundant. But what if your graph is something curvier? For example, what if your function y equals f of x is some curvy graph like this black one here, and at a certain point on this graph, we'll say at this particular x value, you wanted to know the slope of the graph. Loosely speaking, it's the slope of this tangent line, this line that just brushes up against the graph. The problem with trying to find the slope of this red line is if we're looking at only one point on the graph, we have its x value and we can use the function to calculate its y value. But the formula for slope requires 2 points and therefore 2 x's and 2 y's. One x and one y value is not enough information to calculate the slope. So here's where the calculus comes in. To approximate or get an expression to help us find the slope of this red tangent line, the calculus approach is to pick a second point a little further to the right. It could be to the left. We'll just say it's a little bit further to the right. And we're going to use this second point to calculate the slope of this blue line. But if we're going to do that, we need an expression for the second point. Now I could call this one x1 and this x over here x2. And it wouldn't be wrong, but one common approach in calculus to represent this second point isn't to give it a different x name, but rather to measure the distance between the two x coordinates. In other words, if we call the distance here h, then this x coordinate would be this x plus h, and the y coordinate for that point would be the output when we put x plus h into the function, so f of x plus h. Then we set up an equation for the slope of this blue line. The slope of the blue line, and by the way, the blue line is called the secant line. Loosely speaking, a secant line to a graph is a line that goes through 2 points on the graph, as opposed to a tangent line, which locally just touches 1 point on the graph. You could argue that it touches this one over here, but let's just pretend we don't see that. If we want to find the slope of this blue line, we would just set up difference in the y's over difference in the x's. Well, if the red point is the first point and the blue point is the second point, then the second y minus the first y is f of x plus h minus f of x. And if we set up the second x minus the first x, in this case, the blue x minus the red x, the blue x is x plus h, the red x is x, and nothing really happens except in the denominator the x's cancel, leaving just the h in the denominator. And on the top we have the difference in these two y values. So the difference quotient is really just what you get when you set up the slope of a line connecting 2 points on a graph, where the first point's x-coordinate is just called x, but the second point's x-coordinate is alluded to by saying the first x-coordinate plus some distance to give us the second x-coordinate, and of course its second y-coordinate. Calculate the slope, the x's down here cancel, and you're left with the expression called the difference quotient. Now, how does this answer the question, what's the slope of the red line? Well, this is where it becomes a calculus problem. In calculus, you have a mechanism that allows you to ask the question, what happens if I fix this red point, but take this blue point and progressively slide it closer to the red point? In terms of the lines, if we were to move the blue point closer to the red one, then this blue line would start tilting, and intuitively it would become the red line. And the question is, what happens to the slopes as we do that? In calculus, it's something called a limit, and you would take the limit as h approaches 0. In other words, you would let this difference between the x's collapse to 0, forcing the second x to become the first x, forcing the blue point to become the red point, and then seeing what happens to the slope. Now, why can't we just do that directly? Well, if the h was 0, that would cause a problem here. It would also give us 0 in the numerator if you think about it. But let's not push the calculus envelope too terribly far. For those of you who are going into Calculus 1, and I believe this was all of you, you will explore this early, it will be messy, and it will make you reconsider your choice in majors. But as soon as it gets really bad, you start learning some shortcuts, and suddenly calculus becomes easy. So trust me, calculus is real rough at the beginning, and then suddenly it just becomes easy. But let's attack these two functions. Let's attack f of x equals x cubed plus 4x and g of x equals 5 over x, and see if we can calculate the difference quotient. To calculate the difference quotient, you only have to do 3 moves. Move number 1 is to evaluate the function at x plus h, which is sometimes easier, sometimes not as easy. Move number 2 is from that subtract the original function, and then move number 3 divide it all by h. So let's take a look at that for this first example. First, evaluate the function at x plus h, which means we're going to remove all the x's, and if you would like, replace them with empty parentheses. I would highly recommend that. Parentheses cubed plus 4 parentheses. And then substitute x plus h into the parentheses. Now, this would take a little bit of time to clean up, especially here, because you would have to write the x plus h 3 times. Foil these guys, and I'll spare you the details. Foil it, you'll get x squared plus 2xh plus h squared. I believe we did something like that in class, but then we would have another x plus h waiting for it. And meanwhile, after that, we have plus 4 being distributed, so let's go ahead and do that and write plus 4x plus 4h. But then we would have to do a lot of distributing down here. It doesn't matter if we distribute the right into the left or the left into the right. Because the right has only 2 terms, I think it's a little bit easier to write distributing it. The x would get distributed, so with the h, let's do it across the top. That would give you 6 terms. You would have 2 pairs of like terms. I invite you to push the algebra, multiply it all out and gather like terms, but I'll tell you how it's going to turn out. It will turn out to be x to the 3rd power plus 3x squared h plus 3x h squared plus h to the 3rd. And then we have the other 2 terms plus 4x plus 4h. And at that point, there's no more like terms. You can look for them, but they won't be there. Again, I highly recommend pausing the video and verifying that when you cube x plus h, you eventually get down to x cubed plus 3x squared h plus 3x h squared plus h cubed. I'm going to leave out the details for the sake of time. Again, I would highly recommend pausing it and verifying that this is the correct product. At this point, there's nothing left to do for the first move. We have 6 terms right now, but none of them are like terms. So our second move is to do the subtraction. F of x plus h minus f of x. You would think subtraction wouldn't be an issue, and most of the times it isn't. Sometimes the hardest part is figuring out the first part of the subtraction problem, which we just did. And if we give me a moment, I'll write it down again. Okay. But then to subtract the original function means to subtract the entire function. Here's the mistake most people will make. Minus original function. If you were to do that, chances are you made a mistake because the only thing I'm subtracting is the first term and I should be subtracting all of it. The safest way to do that is to put the original function in parentheses upon being subtracted. At that point, it should jump out at you that you have to distribute the negative. So essentially, every term just changes signs. Then you start gathering like terms. What usually happens, especially when your function is a polynomial, is that every term over here that's being subtracted will cancel with something over here. For example, x to the third power minus x to the third power cancels, and 4x minus 4x both cancel, leaving us 3x squared h plus 3xh squared plus h cubed plus 4h. And that's all there is to do in step 2. There's no other like terms to combine. Step 3 is kind of easy, because now all we have to do is divide that by h. Well, in this case, it's pretty easy, as long as you do it correctly. We already know that the difference is 3x squared h plus 3xh squared plus h cubed plus 4h. All we have to do now is put that all over at h and see what happens. Be very careful when you're bringing around, and when you're carrying around a lot of terms. It's easy to make a mistake. Speaking of easily making mistakes, a common mistake here is to say, hey, let me cancel this h with that one, or maybe this h with this one over there. None of those technically are correct. The rule for canceling in a fraction is you can only cancel parts of multiplication problems. Everything up here is currently part of an addition problem and can't be canceled inside of a fraction. The safest thing to do is to factor an h out of the top. If we factor an h out of the top, we're left with 3x squared plus 3xh plus h squared plus 4. All that's over an h, and now the h that we factored out in front is part of a multiplication problem. Since multiplication is the opposite of division, we can cancel those h's, and our difference quotient for that function, I'll write the answer up here just so we can preserve it, is 3x squared plus 3xh plus h squared plus 4. What that formula tells us in the context of the picture that I erased is the slope of that blue line. If you tell me the x coordinate for the first line and the h representing the distance between the two x coordinates, from a calculus perspective, what you would do is let the h approach 0 without getting into details. It boils down to putting in a 0 for the h, and that would give you 3x squared plus 4. In calculus, you'll be practicing this quite a bit. You'll be calculating what's called a derivative, and then you'll learn a quick way to get from here to here almost instantly, and then calculus suddenly becomes easier. So difference quotients are kind of long and drawn out, depending upon the function. This one was a little bit crazy because of the x cubed, but c'est la vie. As far as the other one, 5 over x, it looks like it might be a little bit easier, and in my opinion, it actually is. But some people are intimidated because it has a fraction. How would we do the second one? G of x equals 5 over x. Well, you can start it the same way. The fact that it says g is completely irrelevant. Remember, the name of a function is most of the time arbitrary. Calling this g is no different than calling it f or any other letter besides x. That's already being used. But the 3 steps would be the same. The first thing we have to do is evaluate g of x plus h. Well, that's easy. Take out the x and replace it with x plus h, and you would get 5 over x plus h. By the way, it is not 5 over x followed by plus h. This does not mean stick a plus h on the end of this. This means take out the x and replace it with x plus h. But really, that's all you have to do to find g of x plus h there. It's not a whole lot to do. As far as the subtraction problem, g of x plus h minus g of x. Well, g of x plus h was this, g of x was that, and don't subtract the 5's. You know the rules for, you should know the rules for adding and subtracting fractions. Get a common denominator and then combine numerators. It's not clear whether or not getting a common denominator here is a beneficial move. If you're not sure, do it. It's better to do it and not need to have done it than to have not done it but needed to. Plus, this is a good opportunity to review some algebra skills, like how to add and subtract algebraic fractions, fractions that contain variables and not just numbers. The rule is still the same. Get a common denominator, combine the numerators. But how do you get a common denominator when your fractions are 5 over x plus h and 5 over x? It's actually a lot easier than it seems. Basically, you need to make the denominators match. And the easiest way to do that is to multiply each fraction by the other fraction's denominator on top of itself. For example, the second fraction's denominator is x, so I'm going to multiply the first fraction by x over itself. In the denominator, that will give me an x plus h times x. For the second fraction, I'm going to multiply by the first fraction's denominator over itself, x plus h over x plus h. The reason it has to be over itself is simple. Any value over itself is equal to 1 except 0 over 0. And so by multiplying by an expression over itself, assuming it's not 0 over 0, you preserve the value of 5 over x, you just change its look. And if you notice, the second fraction's denominator is now going to have an x and an x plus h, so it'll have the same denominator as the first fraction. Let's see what happens when we put all this together. Each fraction now has a denominator that contains an x and an x plus h. The first numerator becomes 5 times x, minus the second numerator becomes 5 times the quantity x plus h. And I should probably put this x plus h in parentheses for emphasis, that the 5 is multiplied across all of it. And now my numerator is just begging to get distributed and combined, and we can do it in one move. When we distribute the negative 5 to the x, we'll get a negative 5x to cancel the 5x, so the 5x's cancel, but we'll still have negative 5 times h. So we have negative 5 times h all over the denominator, x times x plus h. So there the algebra was a little tricky because of the fractions, not because we were raising a binomial to a third power. Now we still have one move to go. Step 3 is to take that difference that we just calculated, g of x plus h minus g of x, and put it all over an h. If we do that, we'll have negative 5h over x times x plus h all over an h. And this is what's referred to as a complex fraction, which simply means a fraction inside of a fraction. There's a few ways out of it, but one way to get out of a complex fraction, especially when you only have one fraction on each side, such as this fraction on top and this fraction on the bottom. Oh, you don't see the fraction on the bottom? That's because it's over 1 now. The easiest way out of one fraction on top of another fraction, one fraction on top of one fraction, is to think of it as a giant division problem. Top divided by the bottom, and then execute the rule for dividing fractions, which is to keep the first fraction, in this case keep the top, change it to multiplication, and then multiply by the reciprocal of the second fraction, in this case the fraction on the bottom. It's a pretty standard way out of a basic complex fraction. Basic meaning one fraction on top of one fraction. And look, these h's cancel. Both are parts of multiplication problems, therefore both are eligible to cancel. That was nice. Leaving negative 5 over x times x plus h. The hardest part about some difference quotients is knowing what to do and when to stop. In this case, I would recommend stopping. There's no more simplifying that could happen. Yeah, we could distribute across the denominator, but that's not really going to make anything cancel or anything simplify like it did over there. Again, difference quotients are a thing. You can do function stuff without them, but when you take Calculus 1, you will see them early. You will see them until they make you sick. And then you'll learn to do the results of difference quotients much quicker. And again, just a reminder, from a calculus perspective, the difference quotient is really not the end of the discussion. In calculus, you then follow it up by asking the question, what happens when h approaches 0? Essentially, what happens if I put a 0 here? This would collapse down to negative 5 over x squared. Think about it. And in calculus, you'll learn quick ways to get from, in fact, let me write what I just said. If h, and I'm going to put in quotes, approaches 0, this becomes negative 5 over x squared. And in calculus 1, you'll always conclude a difference quotient with what happens when h approaches 0, which is almost like letting h equal 0, which we couldn't do here ever, and we couldn't do here, but once the h's cancel, we could do. And in calculus 1, you'll learn a quick way to get from here to here. So quick it might take you 30 seconds if you take your time. I promise you, calculus is ugly until it gets easy. I think it's real easy for a while. Ooh, that was a long video. Congratulations, this is the longest short video I've ever made for my video series. Sorry.